So welcome all. So today we are going to start a new session and on this DQ modeling of voltage source converter as part of the course line commutated and PWM rectifiers. So if we look into the course structure, we are now in this part of our course where we are in this three-phase grid connected AC-DC converter with a DQ modeling. So we are going to talk about the DQ modeling and small signal analysis of this grid connected voltage source converter. So first we will talk about the overall control philosophy and then we will go into the modeling part. So let us recap a little bit about the grid connected VSC. As we had talked extensively in the previous lectures that the grid connected VSC, when we use it, we use the primary aim is to exchange a certain amount of active and reactive power with the grid. Okay, so for example, in a PV application we want to send power into the grid, whereas in a battery charging application we want to accept or charge the battery by taking active power from the grid. Similarly, when there is a grid voltage sag, for example, we want to send or we want to inject a little bit of reactive power from the voltage source converter into the grid. So therefore when we talk about the control of this kind of voltage source converter, this is precisely called the grid following voltage source converter. Okay, it accurately follows the grid. Okay, and therefore the aim here is to always have a PG star and QG star. This is this active and reactive power. This thing we use PG star and QG star. This is what we will follow in the course. The star indicates it's the reference here. Okay, so P grid star means the reference active power, QG star means the reference reactive power, which we will exchange with the grid. Okay, so this is the command to the VSC that okay, at this point at t equal to 5 seconds exchange 10 kilowatts of active power. Okay, so PG star will become 10 kilowatt, like that. The same concept also is applicable for motor drive application. It is the model of the converter and the model of the motor is a slightly different. Okay, the plant model gets a little bit different, but the basic philosophy, the control philosophy remains the same. Okay, so for the motor, the voltage source converter has to deliver a certain amount of torque at a certain flux level. Okay, so this is not the aim of the course, so we will not talk about it. However, the philosophy and the understanding of what we are doing in this course can easily be replicated for a motor control application as well. So one who understands a grid control, grid connected converter and its vector control will also understand the motor control, for example a vector control or field oriented control of motor, in a very similar and easy fashion. Okay, so let us start with the grid control converter, and we have to recall the Clark and Park transformation matrix, where we had said that the active and reactive power could be represented in the alpha beta domain or in the DQ domain. Okay, so this we have covered in a previous lecture. Now if you see the overall idea of what we are going to do, so first we look into this part. Okay, this is our grid connected converter. Here is our filter. Okay, and here is the grid, and here is the voltage source converter present here. Okay, so this is basically, if you look from the control point of view, this is our plant. Okay, and here sits our controller. Controller means or a compensator, PI compensator, or which is, this is typically executed in a microcontroller. Okay. Okay, I should not say this word microcontroller is precisely here. I will just use the word that this is the controller here. Okay, and where we have this vector control logic running. Okay, what is the vector control logic we will discuss in this class. But here, so we understand where is the plant and where is the controller, but there are certain other blocks, okay, here, and we will talk about these blocks one by one. So in order to do that, we also apart from that, in this lecture we will develop the dynamic model of the converter. Okay, so the plant dynamic model, as I told you, the VSC connected to the grid with an RL filter is the plant, and so we have to develop the dynamic model of this plant. And after we have developed that, we will see how to design the controller. So how to design controller here, parameters, tuning of this we will see in this lecture. So what is happening here? At first, what is happening is the three-phase AC quantities are converted into two-phase AC quantities. So you can see here there are three-phase quantities. These are precisely the grid currents. Okay, so the grid currents are flowing like this, and so this is converted from three-phase to two-phase. Here you can see this is the TC, Clark's transformation matrix. Okay, so similarly you have the voltages here. These are coming here, the voltages, the grid voltages, and they are also getting converted from three-phase to two-phase. Okay, so there is precisely, I should say, this is, there is another line. So this is where IG alpha and IG beta. Okay, here. So this the three-phase AC quantities are converted into two-phase AC quantities, and this is the first step, and for this we use the Clark transformation. Next step is that we will convert the two-phase quantities into DC. Here you will see these quantities are getting here, this is DC. Okay, in order to do this, as you can recall, when we did a Clark's transformation, we used what is known as a theta, okay, which is given by the PLL, phase lock loop. This gives the value of theta. This theta is useful here in the Clark's transformation matrix. Okay, so once we have done this, we get DC quantities here. So all quantities will now become DC. Okay, now the question that arises is, why have we done that? Okay, why have we converted these three-phase AC quantities into DC? Now there are two reasons for this. Okay, the first reason is that we want the controller working at DC. Okay, because if we have the controller working at DC, we can apply the linear control system theories into this design by using the small signal analysis. So we will have a steady operating point, and over which we will have a small perturbation. Okay, and then based on that small perturbation, we will develop a small signal model of the whole plant, and then apply the linear control system theory. Okay, this is one of the reasons why we actually converted all the three-phase quantities into DC. Because when you go into DC and apply the linear control system theories, we can actually have all the, for example, we will develop the second order, we will develop the whole control system as if like a second order system, and therefore we will understand how much is the bandwidth of the controller, whether there is any zero steady state error or not, whether there is any rejection of disturbance, etc. So we can actually tune these parameters. We can tune how much is the bandwidth of the controller. Okay, how fast it will respond, how quickly it will settle. Okay, the whole plant along with the controller. Okay, how fast is the response of this whole plant. So in order to do this, we have to take all our quantities into DC, and that is why the Clark transformation matrix and Park transformation matrix are useful for us. This is where the usefulness of these two transformations come into picture. There is another reason why we want to do this into the DQ domain. Okay, we are doing it, so therefore we have converted the AC quantities into DC. There is another reason for doing this, is that we can, as we will see in the later slides, we can actually have a decoupled control of P and Q, which means, what is decoupled control? So as I told you, the primary aim of this VSC is to exchange P and Q with the grid. Now, when we say the decoupled control, we can control the P independent of what is happening with Q. So for example, Q can be set to 1 kVA and P can vary from 1 kVA to 1 kilowatt to 10 kilowatt. Okay, so which means that Q is fixed, P is varying, or the other way around, P is fixed, Q is varying. So this kind of an independent control of the active and reactive power exchange with the grid can be done after we go into the DC, I mean in the Parkes transform, after Parkes transformation matrix. Okay, this we will see when we align the D axis with the grid voltage space vector. That is called the vector control of the VSC. So therefore the these blocks here, whatever you are seeing here, these blocks, it appears to be cumbersome initially for any beginner, but once you understand the usefulness of it, you will definitely appreciate why we have done this. Note that these transformations, these are only mathematical transformation using matrices. Okay, we have seen what is Clark transformation matrix and Park transformation matrix. And so with a modern DSP kind of thing, modern DSP like a Texas Instruments DSP or a microcontroller, this is just a mathematical operator and it can be done very fast. Okay, because the microcontrollers nowadays have dedicated multiplication units and they can do this operation very fast. So therefore this operation which we are doing in order to convert the AC quantities into DC is not a very time consuming effort. Okay, it can be done very quickly by the microcontroller. So but now once we have designed our controllers based on the DC quantities, the controller gives some outputs which are again DC. Okay, so this DC now needs to be again converted back to AC. Okay, these are AC quantities. You can see here, these are the AC quantities. VA star, VB star, VC star, if you remember from one of the previous discussions, this is the modulating waveform. Okay, and these are three-phase AC quantities. So what we have done, so after the output of the controller, we must do an inverse Park transformation and inverse Clark transformation. Okay, you can understand here that once I do this inverse thing, then I get back my modulating waveform. After I get the modulating waveform, you can have a PWM here. So in this, you can have sine PWM or you can have space vector PWM. Okay, in this block, which ultimately generates the switching signals for the voltage source converter. Okay, so this is the overall picture. So we start with a three-phase AC quantities here. Okay, and then we go to DC here, and the controller works on the DC, gives the, usually we have a PI compensator here. The PI compensator works on the DC, gives a DC output, which again goes back to the AC. We again go it back, and ultimately PWM pulses to the voltage source converter. Now it is so this is the overall control, closed loop control system. One of the things is that it is also possible to run the closed loop control using Clark's transformation matrix alone. Okay, we may not use this part. Okay, and this is typically done using instantaneous reactive power theory. Okay, you can see in literature instantaneous reactive power, IRP theory. Okay, by the way, what we are working now is, sometimes in the literature it is called SRF theory, okay, synchronous reference frame theory, but there is also, you can do this calculation by using Clark transformation matrix also. Okay, and there you will get P alpha, P beta, I mean in the alpha beta domain. But then there is some issue with that, and that is that the switching frequency of the voltage source converter is not constant. Okay, it starts varying. Okay, so we will prefer to do it in the DQ domain. Okay, we will go into DQ domain and we will develop the controller there itself. But it is possible, and it is also reported many literatures, that the closed loop control of the VSC can be done after class transformation alone. Okay, so we do not need to design PI controllers if you do like that. So that is a little bit advantage on the on this method. But we will follow the traditional DQ control of the voltage source converter. Okay, now next step is that, okay, so we now understand what is the overall control philosophy. Okay, three phase to DC we have to go, and then we have to do this back transformation and all stuff like that. Now before we do anything, the first step of doing this analysis is to model the plant. Okay, so this is our plant here, the voltage source converter. Okay, here you can see the VAN, and this is the filter. So this is the fundamental voltage from the converter, and this is the filter, and this is the grid here. Okay, and we are going to model this plant, right? So we will first write the differential equation. So as you can see, this is the straightforward differential equation for the converter. Okay, so the next step is to transform all these three phase quantities into space vectors. Okay, why space vectors? Because space vectors have been defined, they are defined both at steady state as well as at transients. Okay, phasors are only applicable at steady state. So we have to use space vectors here, because we are now going to deal, or we are going to develop dynamic model of the voltage source converter. And we know what is the definition of space vector. So you take any three phase quantities like this, VAN, VBN and VCN, and multiply with this values and get a 2/3 at the beginning, and then you get what is the space vector for that variable. Okay, so this is, for example, if VAN is the fundamental voltage from the converter, then VConv ABC, I have this is the space vector. Okay, and I have indicated by the bold. Okay, the bold font here indicates that it is a space vector. Similarly, you can have the space vector, this is the grid voltage space vector, and here is the grid current space vector. Okay, so we can develop, we can define the space vectors like this. So of course, when we write these space vectors, the three quantities become now a single space vector equation, and we can write VConv ABC is RIG plus LDDT of IG ABC and VGrid ABC. This space vector, I have always, the subscript always has this ABC. Remember, if you can recall the previous discussion on space vector, recall that the space vectors can be defined in several reference frames. Okay, now we are talking about the ABC reference frame, but space vectors can be defined in alpha beta reference frame. It can also be defined in the DQ reference frame. Okay, so depending on which reference frame, the expression for the space vector will change. Okay, some e to the power j theta angle will start to come. We will see that one going to happen in this case also. But presently we are now defining the space vectors with respect to ABC reference frame. So you can see here, these are the ABC stationary axis, okay, and we are defining the space vectors with respect to these three stationary axes. Here is the converter space voltage space, converter space vector, converter voltage space vector, grid voltage space vector, and grid current space vectors, right? So if I now multiply both the sides with TC, TC is the Clark's transformation matrix. If I multiply both sides, you can see here I have done this multiplication, and if I assume that this system is balanced, then we can now write the converter voltage space vectors in the alpha beta domain, okay, where alpha axis is coinciding with the A axis. So the converted voltage space vector in alpha beta reference frame, so this is what is shown, alpha beta reference frame. The equation is something like this, okay. It is very similar to the equation that we had written in the ABC reference frame, okay. So how does it look like? So here you can see this is the alpha beta reference frame, and we have these space vectors which are rotating, okay. With these space vectors are all rotating, okay. Alpha and beta axis are stationary in space, okay. And this is, here is the equation which we can see here, okay. And what is the equivalent circuit in the alpha beta reference frame? Now you see here, okay. So when we have written this one, okay, of course there is one so there are two equations here. The space vector has been compressed, so there are two equations here. One is V conv alpha and one is V conv beta, right? So, and therefore we have these two okay, these two circuits corresponding to that, because you can see here, if you go back, so V conv alpha, if you take the real part, so V conv alpha, okay, equal to R into Ig alpha plus L ddt of Ig alpha plus V grid alpha, okay. So all with respect to time, okay. So this is one equation, and similarly you can have the V conv beta, right? So Rij beta plus L ddt of, yeah. So in this way you can write the equation, right? So you can see there are two equations which have been compressed and written in a single form, okay. So there are basically, which means that there are two equations and there are two variables here. So you can see this is the V conv alpha and here is the V grid alpha, and therefore we have this R and L here, and the Ig alpha is flowing in the circuit. Now when you do this Clark's transformation matrix, as you can see here, I have taken a picture, a snapshot of that picture. So these three-phase quantities have now become a two-phase quantities here, okay. Alpha and beta quantities are here. So we have V conv alpha and we have V conv beta, okay. So this is here, okay. So so these quantities are all sinusoidal. Remember, when you do a Clark's transformation matrix, the variables are all sinusoidal in nature, okay. Now we will next rewrite the equation in the DQ reference frame. So if you recall the previous diagram, so from this figure we are now moving into the Park's transformation, okay. And for this one we will use the theta, okay. So this is the theta, okay, obtained from the PLL. What is this theta? Theta is basically, you can see, okay, let me see if we okay, theta is the angle, theta is the angle with which the grid voltage space vector is moving, okay, right. So suppose here in the diagram you can see this, here with respect to if this is the stationary axis, the grid voltage space vector is moving, okay, with respect to the stationary axis, and this angle is basically the theta angle, okay, the theta angle, which we will explain later in another phasor diagram and another space vector diagram. Okay, so this theta is needed when we want to do the dq transformation, we want to do the path transformation. Okay, we will need this value of the theta. Now before we do this one, so we are going to apply the we want to change the space vectors which was defined in alpha beta. So for example, if you take the current space vector we have seen, we have defined in alpha beta 0 reference frame. Now we want to change it to the dq reference frame. So you have to recall again, so this is a little bit mathematical, but you have to recall what we had covered some time back in one of the lecture classes, that you can actually move any space vector from one reference frame to another reference frame. So here we are going to move, or we are going to rewrite the space vectors in the dq domain. Okay, we are converting it from the alpha beta reference frame into the dq reference frame, and when we do that, we have to actually multiply with this factor multiplied e to the power minus j theta. It converts one space vector from one reference frame to the other reference frame. So this we have covered previously in one of the lectures, so you have to kind of like go back there. So so this is what we had seen earlier. So we can do the same thing for this equation. So let us do this for this equation which we have seen. Okay, this is the space vector equation in the alpha beta reference frame. So let us do this for this equation. And so when you do that, we are just doing some mathematics here. And so ddt of I dq0, so we are differentiating this quantity, and this will be ddt of this whole thing, which is the product of two variables. So we have to do the differentiation by parts. Okay, so we have to do this one ddt of this one into this one constant, and then ddt of this one, and this becomes the constant. Okay, and doing some simplification, we can get to this equation, which after further simplification, you can do it yourself. We will get that ddt of I alpha beta e to the power minus j theta is ddt of I dq plus j omega, this factor here. Okay, so when we use, so you get this equation and put it back into that space vector. So this one obtained before in one of the slides, and we will introduce insert this one here. Okay, so we write this, we now pre-multiply, we first multiply the entire equation with e to the power minus j theta. You can see here I am multiplying every term with the e to the power minus j theta throughout, and then I get this equation 2 and put it back there, and putting the value obtained in 2, and then I do some mathematics here, and what I get here at the end is this equation. Okay, so this is the equation of the this is the space vector equation in the dq reference frame. Okay, we had got the space vector equation in the alpha beta frame, now we are getting it into the dq frame. So it is very similar to what we had seen in the alpha beta. We have this Ri drop, we had an LDDT drop, and we had a V grid, but there is one term which is coming extra, and that term is this one here. Okay, j omega L Ig dq. Okay, we have to see this one a little bit in details. So with this one, we conclude our session, and I would like to see you once again in another session on the course Line Commutated and PWM Rectifiers.